Okay, I'm going to pick up where I left off in that podcast that you watched that got a little bit truncated. So the thing about the third law is that it says that the the entropy of a perfect crystal is 0 at 0K. The usefulness of that is that S of an element is not 0. Unlike H, and when we get to Gibbs free energy, H and G, they are 0. So S for an element is not 0. And that's because elements have electrons, and as long as you have electrons, you can be disordered. Okay? So S will always be greater than 0 for an element. Okay. Alright, so when we were doing enthalpy, or thermodynamics, kinetics, we were looking at a lot with what's happening with activation energy. Thermo is really not so interested in that. We're really interested in what is this difference between reactants and products. We're interested in this area here, not so much about the activation energy. Okay, so let's take a look at what's going on here. So like you watched in the crash course video, the entropy favors less condensed states. So as you can imagine, as you have gas particles in here that are pretty close together, and then when you open the valve, they move. You have many more, when you have the two bulbs, you have many more arrangements possible for where each of those gas particles can be. So that results in an increase in entropy. Okay? You're more likely, when you open the valve, that you're going to have those particles spread out more, become more disordered. It's kind of like this. It's kind of like a probability model. So if I have 4 particles, there's lots of just 4 particles, and I've got 2 bulbs on my gas container, it is possible that all 4 would be in one bulb or the other, right? But it's more possible that 3 of them will be in one and 1 of them will be in the other, right? Okay? But the thing that's most possible is that 2 will be in one bulb and 2 in the other. And there are lots of possibilities for how that arrangement occurs in terms of whether the red or the blue are together or the green and the yellow. Okay, so this is just an issue of probability. So what's most likely is the most disorder, the most spread out. Okay. All right, so that's the idea behind entropy. Okay, so we predict entropy based on physical evidence. Let me just catch up. Okay, so the greater the dispersal of matter or disorder or spread out or less condensed in a system, the larger the entropy. Okay, the entropy always increases as it changes from solid to liquid to gas, because as you can imagine, the gas is just much more spread out, much more disordered. You know, a solid is very ordered, you know. Particles are nice, neat lattice work. Okay, so when a pure solid or liquid dissolves in a solvent, as you can imagine, you're going to have these particles in a solid that are nice and neatly organized, and a liquid that is pretty well organized. You know, think about water. It's got hydrogen bonds and it's pretty well ordered. When you mix the two together, you end up with separating all of those particles, and now they are just much more spread out, and entropy increases. Now there are a couple of exceptions to that, carbonates included, but for the most part, if I dissolve something, my entropy increases. Okay, if a gas molecule escapes from a solvent, entropy increases. It flies off into space, right? There's lots of different places that particle can be. Okay, so entropy generally increases with increasing molecular complexity. Okay? And this is because there are more moving electrons. Okay? So the more atoms I have, the more electrons I have. The larger the atom I have, the more electrons I have. And the more electrons I have, the more disorder I have. Okay. So when I increase the number of moles of particles, I increase entropy. So if I start off with reactants going to products, and I have, let's say they're all gases, and I start with 2 moles of reactants, and I end up with 3 moles of product, my entropy goes up. Okay? Now you really can't just compare going from a gas to 3 liquids, but within a state of matter you can, if you increase the number of moles, the more stuff you have, the more possible arrangements you have. So the greater the number of arrangements, the higher the entropy of the system. Alright, so let's take a look at a problem here. Let me just catch up to where I am. Okay, so let's see what we can predict. So as I do this, I want you to make a prediction. Alright, so solid sugar is added to form a solution. If I do that, my entropy will go up. Okay, iodine vapor condenses on a cold surface. My entropy will go down. If I do C, let me see. I'm going from a solid to a solid, a liquid, and a gas. My entropy is going to go way up. Here I am going from I have all gases, right? So I'm going from 2 moles of gas on the left with hydrogen 1 here, so that's 3, to 2 moles, excuse me, my entropy goes down. Here, now I forgot to put in here that these PCl5 and PCl3 are solids, so I'm going from a solid to a solid and a gas, making my entropy go up. Okay, so I can calculate entropy from standard table of standard values, just like that reference pack I've been giving you. There are entropys on there. Just be careful. Again, units for entropy are joules per mole Kelvin. Okay, so there is a temperature component to entropy, and it is not in kilojoules. They're not reporting kilojoules like enthalpy in Gibbs energy are. Okay, so be careful of that. Alright, so here we have a problem, and we want to calculate the total entropy. Okay, so I have SO2 plus O2 becoming 2SO3. So the change in entropy is going to equal the sum of the entropy of the products minus the sum of entropy of the reactants. So the products, it's going to be 2 times SO3's value minus 2 times SO2 plus O2's value, 1O2, right? And important thing here is that the entropy of the elements is not 0. So I'm going to have 2 times 256.6 minus 2 times 248.1 plus 205.3, and when I plug and I chug, I get minus 188.3 joules per mole K. Okay. So summary here, if my S is positive, I have more dispersal. It's a more favored, thermodynamically favored condition. If I have S that is negative, I have less dispersal. Okay, so if S is increasing, that is favored. And we'll talk more about how to determine whether a system will be spontaneous or not when we get to the next section. Okay, that's going to do it for us. Alrighty.